Imagine a machine just sitting quietly in your basement,
Right.
and it takes in natural gas from your municipal line or, maybe even pure hydrogen from a tank, and it just strips the energy right out of those molecules.
Without burning anything.
Exactly. Zero combustion, like no flame, no moving parts, absolutely no noise. It just continually spits out clean, highly efficient electricity to power your entire home.
Which sounds like science fiction, but
But the technology actually exists right now. I mean, it is called a solid oxide fuel cell, or an SOFC.
yeah.
But to make that silent, pristine box actually work, the inside of it currently has to operate at a temperature that is like hot enough to literally melt certain types of rock.
Yeah, it's a profound engineering bottleneck, honestly. You have this incredibly elegant electrochemical process, right?
Yeah.
And it promises a revolution in decentralized clean energy, but it is currently caged by this extreme thermal barrier.
Right.
I mean, we are talking about operating temperatures in the realm of 1,000 degrees Celsius.
Which is insane. So, welcome to our deep dive into the source material. Today, we are looking at the literal blueprint for breaking that thermal barrier.
We really are.
We're going to unpack this brilliant stack of scientific research, specifically focusing on the Ph.D. thesis by Muralidhar Girish Chourashiya and several of the related scientific papers based on that doctoral work.
Yeah, it's a fantastic body of work.
The mission today is to basically understand how a highly specific microscopic tweak to a ceramic crystal, combined with a seemingly simple manufacturing trick, could fundamentally change the global energy landscape.
Because the thesis we are exploring, it doesn't just theorize about a solution. It meticulously documents the trial, error, and, ultimate success of engineering a specific material.
Gadolinium-doped ceria.
Exactly. And figuring out how to synthesize it into a microscopic thin film that can operate at half the temperature of traditional fuel cells.
Half the temperature.
Right. It takes the technology out of the realm of, exotic, expensive laboratory curiosities and pushes it directly toward mass commercialization.
So for you listening, whether you are trying to understand the future of the energy grid or you're just fascinated by how scientists manipulate the physical world at the atomic level, we are taking you all the way down to the crystal lattice today.
Oh, way down.
We're going to explore why these machines currently require so much heat, how you can mathematically break a crystal's symmetry to create this, microscopic highway for oxygen.
Which is so cool.
Right. And the chemical paradox that almost killed the project, and the incredibly clever way researchers essentially used high-tech spray paint to solve a massive manufacturing problem.
It's a great story.
We are bypassing the dense jargon, but we are absolutely keeping all the fascinating complex science. So let's start with that 1,000-degree dilemma. If we have this beautiful, silent energy generator, why on earth does it need to run at the temperature of magma?
Well, the heat requirement is entirely dictated by a single component inside the cell, the electrolyte.
Okay.
In a fuel cell, you have an anode on one side where your fuel enters, and a cathode on the other side where, oxygen from the air enters.
Like a sandwich.
Exactly like a sandwich. And right in the middle is the electrolyte. Its sole purpose is to conduct oxygen ions across the gap to react with the fuel while simultaneously blocking the flow of electrons.
Right, because if the electrons just go through the middle...
And you get a short circuit.
Yeah.
So those blocked electrons are forced to travel out through an external circuit. And that flow of electrons, that is the electricity powering your house.
And the industry standard for that middle sandwich layer, the electrolyte, it's historically been this ceramic material called yttrium stabilized zirconia, right? YSZ.
Yeah, YSZ. And YS is incredibly stable, but it is fundamentally stubborn.
How so?
Well, for a solid oxide fuel cell to be commercially viable, that electrolyte needs to allow oxygen ions to flow through it at a very specific rate.
Like a speed limit.
Sort of like a minimum speed limit, yeah.
The consensus in the material science community is that you need an ionic conductivity of at least 0.1 Siemens per centimeter.
0.1 Siemens per centimeter.
Got it. Right. If the conductivity is lower than that, the internal resistance is just too high and the cell can't generate useful power. And here's the kicker. YSZ only achieves that 0.1 Siemens per centimeter threshold when you blast it with 1,000 degrees Celsius of thermal energy.
Man. But I guess it makes sense when you think about heat as just like kinetic energy, right?
Exactly.
Because these oxygen ions, they are locked inside a rigid, solid ceramic structure. They aren't flowing freely like, Salt dissolved in water.
No, they're trapped in a solid lattice.
So to get them to vibrate violently enough to actually break their bonds and hop through the solid crystal, you have to pump a massive amount of thermal energy into the system.
You do.
But running a machine at 1,000 degrees in a residential basement or under the hood of a car, I mean, that just creates an absolute cascade of engineering nightmares. Oh, a total nightmare. The materials required just to house the reaction become astronomically expensive.
Yeah.
You can't use standard stainless steel to connect the individual cells together.
Because it would just melt.
Well, it would oxidize and degrade almost immediately at those temperatures. So you were forced to use exotic, high-temperature alloys.
Which cost a fortune. Plus, you have volatile gases, right, like hydrogen, carbon monoxide, just flowing through the system.
Yeah, highly combustible stuff.
Right. So you had to seal it perfectly so the fuel and the ambient oxygen don't mix and cause a literal explosion. And finding sealants that can remain gas-tight at 1,000 degrees is, I mean, incredibly difficult.
It's a huge pain point. And even if you manage the alloys and the sealants, you hit the ultimate killer of traditional SOFCs, which is thermal mismatch.
Okay, unpack that for us.
So a fuel cell is a composite structure, right?
Mm-hmm.
The anode, the electrolyte, and the cathode are all made of different materials. When you heat the system up to 1,000 degrees, those materials expand. When you power the system down, they contract. But because they are entirely different materials, they expand and contract at different rates.
Oh, I see. It's like pouring boiling water into a cold glass baking dish.
Yes, exactly that.
The inside of the glass expands rapidly while the outside is still cold and rigid, and the internal stress literally tears the glass apart. It just shatters.
Right, and that exact shearing force happens at the microscopic level inside the fuel cell every single time you turn it on and off.
Oh, wow.
Yeah. Over time, the layers warp, microfractures propagate through the ceramic, the gases start to cross over, and the cell just dies. The lifespan is drastically shortened.
Which ruins the commercial viability.
Completely. This is why the entire focus of the research community and, the specific goal of Chourashiya's thesis has been to invent an intermediate temperature solid oxide fuel cell, an ITSOFC.
Okay, an ITSOFC. We were talking about dropping the operating temperature down to, what, the 500 to 700 degrees Celsius range? Still hot, like a commercial pizza oven, but significantly cooler than the melting point of rock.
Right. At 500 degrees, that thermal mismatch is mitigated. You can start using much cheaper steel components.
Right.
The commercial economics finally start to actually make sense.
There's always a but. The moment you drop the temperature, our old friend, the YSZ electrolyte, just freezes up.
Yep. The kinetic energy drops. The oxygen ions stop hopping, and the conductivity plummets well below that magic 0.1 threshold.
So YSZ cannot function efficiently in the intermediate temperature range.
It's useless there. To build an ITSOFC, researchers had to fundamentally abandon the standard material and find a completely different atomic scaffolding.
And this is where the research turns to a material called cerium oxide, or ceria.
Right. Enter ceria.
So let's visualize this new atomic scaffolding. Pure ceria has what material scientists call a fluorite crystal structure.
Yeah, so imagine a perfectly repeating three-dimensional grid. In this grid, the cerium ions, which carry a strong positive charge of 4+, are locked into a specific, widely spaced arrangement. Nestled into the empty spaces of that scaffolding are the oxygen ions, which carry a -2 charge. The crucial difference between ceria and the old YSC is the physical distance between the atoms. Ceria has a naturally larger unit cell.
The structural foundation is literally wider.
Yes.
So if the old YSZ crystal was, I don't know, a building with narrow, cramped hallways, ceria is a building with wide, spacious corridors. It is physically easier for an oxygen ion to squeeze through the gaps in ceria.
Exactly. Those wider channels drastically lower the activation energy required for an oxygen ion to move.
But just having wide corridors doesn't mean the ions are actually going to travel.
Right, because the structure is naturally stable and perfectly packed. To get the oxygen to move, you have to intentionally break that perfection. You have to introduce an impurity.
And this is the concept of doping.
Yes.
The researchers took pure ceria and mathematically introduced gadolinium. They are physically swapping out some of those cerium atoms in the lattice and replacing them with gadolinium atoms to create gadolinium-doped ceria, or Gd-C. But why gadolinium? I mean, it comes down to a deliberate electrical imbalance, right?
It does. It's all about the valency. Cerium ions have a valency of 4+ food. Gadolinium ions have a valency of 3+ fin.
Okay, 4 versus 3.
Right. When you force a 3+ gadolinium ion into a spot that is supposed to hold a 4+ cerium ion, The overall crystal lattice suddenly finds itself lacking positive charge.
The crystal is mathematically unbalanced, and nature, especially at the atomic level, violently hates an electrical imbalance.
It will do anything to fix it.
So to compensate for the missing positive charge, the lattice is forced to expel something negative. So for every 2 gadolinium-3 plus ions you swap into the structure, the crystal kicks out 1 oxygen-2 ion just to balance the books and remain electrically neutral.
Exactly. And when that oxygen ion is expelled, it leaves behind a physical void in the crystal structure. We call these extrinsic oxygen vacancies.
Oxygen vacancy.
And these vacancies are the entire secret to solid-state ionic conductivity.
Okay, so if we imagine the crystal lattice as like a crowded room full of people sitting in chairs, the cerium atoms are the people. By swapping in gadolinium, we are essentially walking through the room and randomly yanking chairs out from under people.
That's a great way to picture it. You're creating empty seats.
Right. And an oxygen ion moves across this solid ceramic, not by flowing like water, but
Right.
by jumping from its current seat into an empty chair next to it.
Exactly. The oxygen ions hop from vacancy to vacancy, and because ceria already has those wider, more spacious corridors we mentioned, and now you have artificially seeded the material with millions of these empty chairs.
They can just move so much faster.
Right. The oxygen ions can cascade across the material at incredibly high speeds, even when the thermal energy, the temperature, is significantly reduced.
Man, it is a brilliant piece of atomic engineering. But I have a question.
Sure.
If pulling chairs out of the room creates empty spots that make it easier for the oxygen to hop, logic would suggest that you should just keep pulling out chairs.
Right, you'd think so.
Yeah. If you want maximum conductivity, shouldn't you dope the ceria heavily? Like remove 30, 40, maybe 50% of the cerium?
That is the exact hypothesis that many researchers, including the author of this thesis, had to rigorously test. The source material details how they synthesized different batches of the material to find the optimal recipe.
Okay.
So they created Gd-C10, which is ceria doped with 10% gadolinium, but they also created Gd-C20 and Gd-C30.
And what happened? Because the physical testing actually shattered that initial logic, right?
It completely shattered it. The 10% gadolinium badge Gd-C10 provided the absolute maximum ionic conductivity. As they pushed the doping higher to 20% and 30%, the oxygen ions actually slowed down. The conductivity collapsed.
Well, why?
The mechanism behind that collapse is known as the solute drag effect, and it exposes the physical trade-off of doping.
Okay.
You are focusing on the empty chair, but you have to look at the person you left standing next to it. A gadolinium ion has a larger ionic radius than a cerium ion. It is physically wider.
Ah, so you are creating an empty spot, but the impurity you used to create it is bulging out into the corridor.
Precisely. When you keep the doping low, around 10%, the vacancies far outweigh the physical disruption. But when you push it to 20% or 30%, you are packing the lattice with these oversized gadolinium ions.
You're right.
They distort the surrounding crystal structure.
Mhm.
They physically impinge on those wide corridors that made ceria so attractive in the first place.
So the oxygen ions might have plenty of empty chairs to hop to, but the path to get there is now blocked by these bulky structural pillars.
Exactly. The energy required for the oxygen to squeeze past the gadolinium, the ion migration enthalpy, it just spikes.
It creates a microscopic traffic jam.
It does.
And it doesn't just happen inside the crystal itself. The research notes that higher concentrations of gadolinium fundamentally changed how the ceramic formed when they baked it.
Yeah, it altered the microstructure entirely. Solid ceramics are made up of millions of microscopic grains squished together. The boundaries where one grain meets another are called, quite intuitively, grain boundaries.
Yeah.
And they act as natural resistance points, like toll booths on a highway. The researchers observed that adding too much gadolinium actually inhibited the growth of these grains.
Meaning the grains stayed very small.
Yes.
And if you have a material made of millions of tiny grains instead of a few large ones, you inherently have vastly more grain boundaries. You've just built thousands of extra toll booths.
That's a perfect analogy. The excess dopant actually segregates and clumps up at those grain boundaries, making the toll booths even harder to pass through. So 10% doping is the definitive mathematical sweet spot.
Gd-C10.
Gd-C10. It maximizes the number of oxygen vacancies while keeping the physical distortion of the crystal and the suppression of grain growth to an absolute minimum. Gd-C10 is the champion material that theoretically hits that magic 0.1 conductivity mark at lower temperatures.
And of course, science rarely lets you off that easily.
Never.
Just as they established Gd-C10 as the perfect ionic conductor, they slam into this fundamental chemical paradox inherent to ceria itself. a paradox that threatens to make the material completely useless inside a working fuel cell.
It is the Achilles heel of ceria, and it is entirely driven by thermodynamics. We have to look at the environment inside an operating fuel cell.
Okay, let's look at it.
On the anode side, where the fuel, like hydrogen or natural gas, is reacting, the environment is fiercely demanding. The fuel is constantly consuming oxygen to create water and electricity.
Right.
This creates a zone with an extremely low oxygen partial pressure.
It is a highly reducing environment. I mean, it is essentially a vacuum constantly trying to suck oxygen out of anything nearby.
Including the electrolyte itself.
Oh, wow.
Yeah. When pure ceria or GD-C is exposed to that intense reducing environment at high temperatures, the thermodynamics shift. The oxygen atoms inside the ceria crystal lattice are tempted to leave.
They want to jump out.
Exactly. And when an oxygen atom actually breaks free and escapes into the gas phase, it leaves something critical behind inside the lattice. Its electrons.
Because the oxygen originally had a 2 charge, but it escapes as neutral O2 gas. So those 2 negative electrons are just left stranded inside the ceramic structure.
And those stranded electrons immediately seek out the positively charged cerium-4+ ions. The cerium absorbs the electrons and is chemically reduced down to cerium-3+ ion.
Which sounds like a minor chemical curiosity until you realize what those freely moving electrons do to the function of the machine.
It's devastating.
Right, because the entire premise of a solid electrolyte is that it must be an absolute impenetrable wall to electrons. It can only allow ions to pass. If it allows electrons to flow through it, they just take the shortest path from the anode to the cathode, entirely bypassing your external wire.
It creates a massive internal short circuit.
Yeah.
When the cerium reduces to 3+ ion, the material gains electronic conductivity. The electrons flow straight through the ceramic, the voltage collapses, the power output drops to near zero, and your highly efficient power plant essentially becomes a very expensive, very useless brick.
Man, so here is the brutal paradox the researchers faced. The chemical reduction of cerium is driven by heat. If you operate the fuel cell at 800 or 900 degrees Celsius, the ceria reduces heavily and it short circuits. To stop the reduction and force the ceria to remain a pure ionic conductor, you must drop the operating temperature down to 500 degrees Celsius. But if you drop the temperature to 500 degrees to protect the chemistry, the thermal kinetic energy plummets.
Exactly. Even with our beautiful 10% gadolinium sweet spot, the oxygen ions lose the energy they need to hop quickly from vacancy to vacancy across a thick piece of ceramic.
So the ionic conductivity drops below the threshold.
You're stuck. If it's hot enough to conduct ions, it short circuits. If it's cool enough to prevent the short circuit, it can't conduct ions.
It's a complete catch-22. You can't change the laws of chemistry, and you can't alter the valency of the atoms. So the only variable left to manipulate is the physical geometry of the material itself.
And that's exactly what they did. If the ions are moving too slowly at 500 degrees to successfully cross a thick ceramic pellet, you have to shorten the journey. This is the genesis of the thin film strategy.
Right. The researchers deduced that they didn't need to force the ions to move faster, they just needed to give them a much shorter racetrack.
In physics, we refer to this as reducing the ohmic losses. Electrical resistance is directly proportional to the thickness of the material.
Okay.
By shrinking the Gd-C electrolyte down to an astonishing 10 to 20 micrometers, which is a fraction of the width of a human hair, the physical distance the ions have to travel becomes negligible.
So the resistance just plummets.
Exactly.
And because the resistance is so low across that microscopic gap, the cell can easily achieve that magic 0.1 Siemens per centimeter performance, even at a sluggish 500 degrees Celsius, completely bypassing the temperature zone where the cerium would reduce and short circuit.
It is an incredibly elegant workaround. It perfectly balances the chemical constraints with the electrical requirements.
It really is. But it introduces an entirely new, incredibly daunting challenge. Synthesizing a perfect, flawless, gas-tight crystal layer that is only 13 micrometers thick is exceptionally difficult.
Oh, it's a massive manufacturing hurdle.
But before the researchers could even attempt to make the thin film, they first had to prove they could synthesize the base Gd-C powder perfectly without ruining it.
Right, you have to make the paint before you can paint the wall.
Exactly. Which brings us to the kitchen. How do you actually bake a batch of microscopic 10% gadolinium-doped ceria? The thesis details a fascinating progression of trial and error here, comparing the traditional solid-state reaction method against a much newer, wilder technique called the glycine nitrate process.
Yeah, let's look at the old school solid-state method first.
Let's do it.
The solid-state method is kind of the blunt instrument of material science. You purchase commercial cerium oxide powder and gadolinium oxide powder. You weigh them out precisely to hit that 10% atomic ratio, and you physically grind them together in a ball mill for hours to mix them as thoroughly as possible.
Just mashing rocks together.
Basically. Then, you press that mixed powder into a pellet and you bake it.
But baking is a wildly inadequate word for what happens next, right?
Very inadequate.
Because you are trying to force solid particles of two different materials to completely fuse together at the atomic level and rearrange themselves into a single, flawless fluorite crystal lattice.
Which is not easy.
No. To force solid matter to diffuse like that, you have to subject it to extreme, punishing heat. The thesis notes they had to sinter these pellets at 1773 Kelvin.
That is approximately 1,500 degrees Celsius, and they hold it at that temperature for hours. The ultimate goal of this extreme heating is density.
Okay, density. Why is that so important?
For this material to function as an electrolyte, it cannot have microscopic holes in it. If it is porous, the hydrogen fuel and the ambient oxygen will simply seep through the physical gaps, mix, and combust, destroying the cell.
Oh, right. Boom.
Exactly. It must achieve a relative density of well over 90%.
And the extreme 1,500-degree heat did the job mechanically. They achieved a highly dense 94 to 98% rock-solid pellet. The grains merged, the pores closed up.
Yeah.
And this is a massive, but we already established that ceria absolutely hates extreme heat.
Yes, the irony is unavoidable.
Yeah.
The very temperature required to physically densify the ceramic was simultaneously triggering the exact chemical disaster they were trying to avoid in the fuel cell. At 1,500 degrees, the cerium-4+ began to reduce down to cerium-3+, right there in the furnace.
The researchers actually confirmed this, right?
They did. When they ran X-ray diffraction, which essentially maps the atomic structure of the material on the solid-state pellets, they detected traces of C2O3.
Oh, wow.
The material was degrading before it ever even made it into a fuel cell.
Wow.
They had to invent this excruciatingly complex, multi-step baking profile, including a delicate binder burnout phase at 30 degrees, just to try and protect the chemistry while still getting the density.
It just proved that solid-state synthesis is fundamentally antagonistic to ceria. You are fighting the material's innate thermodynamics every step of the way.
Every single step.
And this realization pushed the researchers toward a completely different paradigm, right? Soft chemistry, specifically the glycine nitrate process, or GNP.
GNP. This is where the chemistry gets genuinely dramatic.
I love this part.
Instead of grinding dry, stubborn powders together, they dissolved metal nitrates, cerium nitrate, and gadolinium nitrate into pure water.
Okay, liquid.
Right. Now you have the individual atoms, perfectly homogeneously mixed at the molecular level in a liquid solution. Then they added glycine to the water.
Wait, glycine, like the simple amino acid.
Yeah, exactly. But in this contest, it serves a dual purpose. It acts as a complexing agent, binding the metal ions together in the liquid so they don't separate out. But more importantly, glycine contains carbon and hydrogen. It is an organic fuel.
Oh boy.
And the metal nitrates, on the other hand, act as powerful oxidizers.
So you have a fuel and an oxidizer perfectly mixed in a beaker of water.
Yes.
They heat the liquid on a hot plate. The water gradually boils off and the liquid thickens into a viscous gel. And then as the temperature continues to rise, autoignition.
Boom.
The gel literally combusts. It is a highly localized, self-sustaining exothermic reaction. The temperature spikes instantaneously, and the glycine fuel burns violently with the nitrate oxidizer.
And this reaction produces a massive volume of gases, carbon dioxide, nitrogen, water vapor, which violently tear the forming solid apart from the inside out.
And the result is incredible. Instead of a dense, hard clump, the combustion leaves behind a voluminous, incredibly fine ash. It is a highly pure nanocrystalline powder.
Nanopowder.
Right. We are talking about particle sizes of around 20 nanometers. To put that in perspective, a sheet of paper is about 100,000 nanometers thick.
It's unimaginably small. And this staggering reduction in particle size changes the entire physics of the baking process.
How so?
Because the particles are so infinitesimally small, they have a massive amount of surface area relative to their volume. They possess immense surface energy. They are desperate to fuse together to lower that energy state.
Okay, I think I have an analogy for this. Imagine trying to pack a glass jar with large, jagged landscaping rocks.
Okay.
No matter how hard you push, there are going to be massive air gaps, right? porosity.
Really are.
To get those rocks to melt together and fill the gaps, you'd need the 1500-degree heat of a volcano. But now, imagine packing that same jar with ultra-fine, powdery baby powder. The powder naturally settles in and packs together incredibly tightly.
That is the exact mechanical advantage of the nanopowder. Because the initial packing density is so much higher and the surface energy is so intense, the researchers found they could sinter these nanopowders into solid, leak-proof pellets at a much, much lower temperature.
Like how much lower?
They achieved over 95% density by baking the material at just 1200 degrees Celsius.
They dropped the baking temperature by 300 degrees.
Exactly, which meant they completely sidestepped the chemical reduction. The cerium stayed firmly in its 4+ state. They had successfully proven they could synthesize the absolutely perfect batch of GD-C10. The fundamental bulk material worked.
But a bulk pellet is not what we need, right? Well, you talked about this. A thick pellet guarantees high ohmic losses and terrible performance at 500 degrees.
Right, the 13-micron thin film.
Exactly. They had perfected the paint, but now they had to figure out how to lay it down in an impossibly thin layer without using, like, billion-dollar microchip factories.
Which ushers us into the most ingenious engineering feat of the entire thesis, the spray pyrolysis technique, or SPT.
This is literally painting with molecules.
It really is. To appreciate the brilliance of SPT, you have to understand the current commercial alternatives. If you want to create a highly controlled microscopic thin film of a complex crystal, say, for an advanced solar panel or a semiconductor, the industry standard relies on vacuum deposition, techniques like chemical vapor deposition or sputtering.
Okay, and what does that look like?
You're talking about massive stainless steel vacuum chambers, high-energy lasers or electron beams to vaporize the source material, and pristine, clean rooms. It is incredibly precise, but it is astronomically expensive and incredibly slow to scale up for mass manufacturing.
And if the goal is to put a solid oxide fuel cell in the basement of every house and under the hood of commercial trucks, you cannot rely on bottlenecked million-dollar vacuum chambers to manufacture the core components. You need a process that is continuously scalable, operates in the open air, and uses cheap equipment.
Exactly. Spray pyrolysis is the answer to that economic reality.
It honestly sounds almost too simple, almost crude, to work for something this advanced. The researchers took those exact same cerium and gadolinium nitrates from the combustion experiment and dissolved them into double distilled water, dialing in the perfect 9-to-1 atomic ratio for Gd-C10.
Yep.
And then they essentially loaded it into a high-tech airbrush.
They did. They used an air blast nozzle to atomize the liquid precursor into an incredibly fine mist. They aimed that mist at a heated substrate, essentially a precisely controlled hot plate.
Which sounds crazy. You are spraying salt water onto a hot frying pan. Usually when you do that, the water sizzles off and you are left with a random crusty white stain of amorphous salt.
Right, but the physics of spray pyrolysis are governed by precise temperature control. The substrate is heated to precisely the decomposition temperature of the nitrate salts, which for these specific materials is around 280 degrees Celsius.
280 degrees.
When the microscopic droplet of water hits that heated surface, a rapid sequential microreaction occurs. The water evaporates instantly. The remaining nitrate salts immediately hit their decomposition threshold and break down.
And here's the magic. Instead of forming a random crust, the released cerium, gadolinium, and oxygen atoms instantly self-assemble.
It's beautiful.
The thermal energy from the substrate gives them just enough mobility to click into their most stable energy state, which is that perfectly repeating cubic fluorite crystal lattice.
You're constructing a flawless ceramic crystal structure, molecule by molecule, layer by microscopic layer, in the open air. No vacuums, no lasers, just atomized water and a hot plate.
It is a staggering breakthrough for the cost-effective mass manufacturing of advanced ceramics.
It's game-changing. The researchers proved the concept worked by spraying the solution onto a plain glass slide. The crystal formed perfectly. Then they leveled up and sprayed it onto a dense pellet of GD-C, and it formed beautifully there too.
But an electrolyte sprayed onto glass or onto more electrolyte is basically useless, right? To build a functioning fuel cell, that 13-micron thin film has to be sprayed directly onto and fundamentally bonded with the anode.
And the anode is a completely different beast.
Okay, tell me about the anode.
The industry standard anode for these intermediate temperature fuel cells is a composite material made of nickel oxide in GD-C, referred to as NiO-GD-C. It is designed to be highly porous so the hydrogen fuel can flow through it to reach the electrolyte.
Okay, so the researchers aimed their perfectly tuned spray nozzle at a heated pellet of this Gd-C anode composite. They sprayed the film.
And it was a complete catastrophic failure.
Oh no, what happened?
The film wouldn't stick.
Yeah.
The mechanical bond failed entirely. Well, the Gd-C substrate, in its pre-fired state, was too dense and smooth. As the atomized droplets hit the 280-degree surface and instantly crystallized, the ceramic film contracted slightly. Without any physical grip on the smooth substrate below it, the internal thermal stresses of the crystallizing film caused it to warp, crack, and flake right off the surface.
Man. So they had perfected the spray, but the canvas was entirely rejecting the paint. How do you force a microscopic contracting crystal to adhere to a surface that refuses to hold it?
This is where the researchers had to pivot from material synthesis to brilliant interfacial engineering.
Artificial engineering.
Yeah, they couldn't change the chemistry of the spray without ruining the electrolyte, so they had to fundamentally alter the physical topography of the target.
They had to change the canvas.
Exactly. They took the Gd-C anode substrate and, before putting it under the spray nozzle, they placed it in a furnace flooded with hydrogen gas and baked it at 900 degrees Celsius for 5 hours.
Wait, hydrogen gas is highly reducing. If you pump a reducing gas over nickel oxide at 900 degrees, it's going to aggressively attack the material. It's going to strip the oxygen atoms right out of the nickel oxide matrix, isn't it? You'd be left with pure metallic nickel.
That is exactly the chemical reaction they were weaponizing.
Really?
Yes, the hydrogen stripped the oxygen out of the NaO, reducing it to pure metallic nickel. The substrate transformed from NiOGdC to NiGdC. But when you violently rip oxygen atoms out of a solid crystalline matrix, you leave behind massive physical voids.
Oh. The surface of the substrate is suddenly riddled with microscopic craters. It transforms from a dense, smooth ceramic into a highly porous, rough metallic sponge.
In material science, we call this creating nucleation sites. By chemically reducing the substrate, they engineered millions of microscopic nooks and crannies for the spray to grip onto.
They essentially sanded the wood with extreme prejudice before applying the paint.
Exactly. But they didn't stop there. They realized that if they just sprayed the liquid at the normal 280 degrees, the droplet would still vaporize the instant it touched the surface, forming a dry crystal before it could ever sink into those new craters.
Right, it would just sit on top.
So they completely altered the parameters of the spray process itself. They dropped the temperature of the heated substrate down to 250 degrees Celsius.
And 250 degrees is a critical threshold, right? It is below the decomposition temperature of the cerium and gadolinium nitrates.
Precisely. When the atomized droplets hit the substrate at 250 degrees, the water still evaporates. But the salts do not instantly decompose into a dry ceramic crystal.
So what do?
Instead, they land and accumulate as a wet, semi-solid, highly viscous precipitate.
The thesis calls this precipitative deposition.
Yeah.
Because the spray lands wet, it has the physical time and fluidity to seep deep down into all those newly created rough, porous craters of the metallic nickel sponge. It physically embeds itself into the substrate.
It really gets in there. Once they have built up a thick enough layer of this wet precipitate, they take the entire assembly, the rough metallic substrate coated in the wet precursor, and they place it into a standard furnace at quiescent degrees Celsius, exposed to ambient air.
And the furnace triggers a magnificent, synchronized culmination of everything we've talked about. 3 distinct transformations happen simultaneously.
Let's break them down.
First, any lingering moisture is violently boiled away. Second, the precursor salts, which are now physically locked deep inside the pores of the substrate, finally hit their decomposition temperature and crystallize into that perfect Gd-C fluorite lattice.
It is literally blooming out of the cracks, creating an unbreakable mechanical root system.
It's like pouring wet concrete over a complex web of steel rebar rather than just stacking dry bricks on top of it.
The mechanical interlocking is profound. But the third reaction is what locks the trap. Remember, they are baking this in ambient air, which is full of oxygen.
Okay, yes.
That pure metallic nickel sponge, when exposed to oxygen at 1,000 degrees, immediately oxidizes back into nickel oxide.
And when a metal oxidizes, it physically expands.
Yes. The nickel oxide swells as it incorporates the oxygen. As it expands, the pores of the substrate physically shrink, clamping down with immense microscopic pressure on the roots of the GDC crystal that just formed inside them.
That is a staggering piece of engineering. They chemically manipulated the substrate to make it rough, they applied the precursor wet so it would soak into the wounds, and then they used heat to simultaneously crystallize the film and force the substrate to swell up and swallow the film's roots.
The electron microscopy images provided in the thesis are absolute proof of this success. When you look at the cross-section of the final piece, you see a flawlessly integrated, beautifully dense film of gadolinium-doped ceria bonded directly to the porous Gd-C anode.
That's incredible.
There is no delamination. The interface is continuous.
And the thickness of that flawlessly bonded film, just 13 micrometers, a fraction of a hair. And crucial to the entire endeavor, it had a relative density of over 96%. It was entirely free of cracks, meaning it was completely gas-tight.
They successfully manufactured a complete half cell for an intermediate temperature solid oxide fuel cell. They created an ultra-thin, highly dense, perfectly doped solid electrolyte bonded to a porous anode.
And they did it without a single expensive vacuum chamber, utilizing cheap spray nozzles, and the entire assembly was finalized at a relatively mild 1,000 degrees Celsius, completely avoiding the high-temperature degradation of the ceria.
Which brings us to the ultimate question. Did this incredible journey of atomic manipulation, thermodynamic dodging, and chemical spray painting actually result in a working power source?
Exactly. Did it work?
The researchers took this completed half cell and put it through rigorous electrical testing. The primary diagnostic tool they used is a technique called electrochemical impedance spectroscopy, or EIS.
Yes. Okay.
It is a fascinating way to interrogate a material. Instead of just pushing a steady direct current through the cell, EIS shoots alternating current through the material, and it sweeps across a massive range of different frequencies, from high-frequency rapid pulses to slow, low-frequency waves.
Why alternate the frequencies? What does that show you that direct current doesn't?
It allows you to isolate the different types of traffic jams inside the material. High-frequency current moves so fast that it only really interacts with the bulk interior of the crystals, the wide corridors and empty chairs we talked about.
Okay.
But as you slow the frequency down, the current starts to interact with the grain boundaries, the toll booths. By measuring how the material resists the current at different frequencies, the researchers can mathematically untangle the exact source of the resistance.
Oh, that's so smart. They can definitively prove whether the ions are struggling to move through the crystal itself or if they are getting backed up at the borders.
Exactly.
And when they ran this analysis on the 13-micron thin film, the grain interior conductivity, the speed of the ions moving through the lattice, was exceptional.
The mathematical target, remember, was 0.1 Siemens per centimeter.
Yeah.
The EIS testing confirmed that the 13-micron GD-C10 film hit approximately 0.1 Siemens per centimeter at exactly 500 degrees Celsius.
They hit the commercial viability threshold at literally half the temperature of the old YSE standard. They shattered the 1,000-degree thermal barrier.
It's a huge milestone.
But conductivity is only half the battle, right? They still had to prove that dropping the temperature to 500 degrees had successfully prevented the ceria from chemically reducing and creating that catastrophic electronic short circuit.
Right, the short circuit problem.
Yeah.
To prove that, they placed the material into what is called a symmetrical cell configuration. They essentially capped both sides of the electrolyte and measured the open circuit voltage, or OCV.
OCV is basically the electrical pressure of the system when it is just sitting there fully fueled but no current is being drawn from it, like measuring the water pressure in a hose when the nozzle is closed.
Exactly. If the electrolyte has microscopic cracks and is leaking gas, the pressure drops. But more importantly, if the cerium had reduced to 3+, and the material was allowing electrons to leak through the ceramic, the voltage would plummet.
Okay.
A high OCV means the material is perfectly dense and is acting as an absolute impenetrable wall to electrons.
And the thesis records an OCV of 0.85 volts at 500 degrees Celsius, which the author notes is remarkably high, outperforming many previously published attempts at ceria-based thin films.
That 0.85 volt measurement is the definitive victory of the thesis. It proves that the thin film precipitative deposition technique created a mechanically perfect, gas-tight seal, and that operating at 500 degrees completely neutralized the electronic short-circuiting problem. The blueprint is theoretically sound, physically manufacturable, and electrically verified.
And this brings it all back to why this matters to you listening right now. This is not just abstract chemistry confined to a university library. The work in this thesis is the literal architectural plan for the next generation of the power grid.
It really is.
When you can successfully operate a highly efficient fuel cell at 500 degrees instead of 1,000, you strip away the need for exotic aerospace alloys. You strip away the catastrophic thermal fracturing. You can build the housing out of standard, cheap ferritic steel.
You dramatically lower the manufacturing cost, and you massively increase the operational lifespan. It makes the technology consumer-ready. It makes the silent zero combustion basement power plant a distinct economic reality.
And it was all achieved by understanding the world at an almost unimaginably small scale. We started with the sheer brute force of extreme heat-melting YSC ceramics.
Right.
We moved into the atomic architecture of ceria, realizing that if we strategically swapped in 10% gadolinium, we could yank just enough chairs out of the crystal lattice to let oxygen ions sprint through without crowding the hallways.
We navigated the thermodynamic minefield of chemical reduction by refusing to let the fuel cell operate above 500 degrees, which forced us to shrink the entire highway down to a 13-micron thin film to minimize the resistance.
We bypassed the 1,500-degree material-destroying baking process by using the explosive glycine nitrate combustion to create hyperreactive nanopowders.
And finally, we solved the ultimate manufacturing hurdle by treating a dense ceramic, like a piece of wood, chemically sanding it with hydrogen to create rough pores, and then spray painting a wet precipitate that rooted itself deep into the matrix before the substrate expanded to lock it in forever.
The progression of problem solving is a masterclass in material science, but the implications of Chourashiya's spray pyrolysis breakthrough extend far beyond just fuel cells. And this raises an incredibly provocative thought to leave you with.
What else can we build with this?
Yeah, what else?
If we have definitively proven that we can flawlessly manipulate complex crystal lattices and deposit them seamlessly as incredibly thin, highly dense films, using something as cheap and scalable as an atomized water spray on a hot plate, what other industries are about to be upended?
Right.
Think about advanced solid-state batteries for electric vehicles, which currently struggle with the massive costs of thin film deposition, or next generation, ultra-efficient perovskite solar cells.
Technologies that are currently bottlenecked by the requirement for million-dollar vacuum chambers in clean rooms could suddenly be manufactured on continuous open-air assembly lines.
The chemistry of the future has largely been solved in the lab. The real battle has always been the manufacturing. And this thesis strongly suggests that the manufacturing barrier is crumbling.
It is a profound shift. The high-tech, pristine energy systems of the future might not be built in billion-dollar silicon foundries. They might be sprayed onto hot steel plates in highly efficient, low-cost factories.
It's an exciting thought.
It is an incredible thing to consider. When we look out at the landscape of clean energy, it is so easy to focus on the macro. The massive wind turbine blades sweeping through the air, the sprawling multi-acre fields of solar arrays. But the real revolution, the silent, ultra-efficient engine of the future we've been waiting for, it's happening in the invisible microscopic spaces between atoms.
It really is.
The dense, muddy waters of high-temperature engineering are finally clearing up, one 13-micron layer at a time. Thank you so much for joining us on this deep dive into the source material. The next time you flip a light switch or start your car, take a moment to look at the energy technology around you and appreciate the invisible, atomic-level engineering that makes our modern world possible. We will see you next time.